talk to you a little bit more about gravitation. In particular, I want to talk to you, my comments at the moment are targeted towards the issue of gravitational potential energy. So, I have a confession. Confession to make. The confession that I have to make to you is that, what I told you earlier this semester was a lie. It was a lie. So this formula, that the potential energy due to gravity was mgh, well, that's just not really true. I mean, that's not quite right. It's not quite right. So let me tell you the real story. So the real story, and even this isn't really the real story, but it's the best story we could tell with the mathematics we have here. So we have the gravitational force, just focusing on the radial direction, is equal to what? It's g m, mass of the Earth, let's say, divided by r squared, right? And just to be clear, if I put the Earth at the center of the universe, then I need a minus here, right? Because it's attractive. So there you go. Now, so what would a potential energy function be? A function that I can take the gradient of, right? Nabla, if you like. So minus the gradient of the potential energy function, let's say u, should give me back that, right? So what that tells me, integrating both sides, is just that I should have u as a function of r is equal to some constant u naught plus g m mass of the Earth divided by r. Now let's see. Just to check me mathematically, what do you got to do? You got to take the gradient. The gradient of u is going to be partial u, partial r hat. All right, plus stuff, theta hat, plus other stuff, phi hat. You can try to fill in those parentheses with your standard calculus book. You will fail, because for some reason, we as a mathematical community don't think that you guys need to know that in your Calc 3 class. I don't understand why that is, but in spherical coordinates, these are somewhat complicated. What goes here, somewhat complicated, okay? But rest assured that it involves partial u, partial theta, and partial u, partial phi. So it involves the azimuthal and polar angles. But as you can see, there's no dependence on either of the spherical angles here, right? So certainly you don't need a theta or phi dependence in your u. So basically those, and because you don't have a phi hat or a theta hat term, so these, both of these are 0. We don't worry about them. So we can just really think about it one-dimensionally. Basically, we just have to solve this problem of one-dimensional calculus, namely that the u, because if u is only a function of r, then partial u, partial r is du dr. So we just have to solve du dr is equal to, g m, big M, over r squared. So you integrate both sides, and you get the u that I just wrote down. And there you go, there's a derivation of the gravitational potential energy. Now, typically speaking, what do we set u naught equal to? It's a constant, right? You can make it whatever you like. So if I'm working for problems with planets and things, I usually take u naught equal to 0. So comment, if you set u naught equals to 0, that tells you that u of infinity is equal to 0, right? So basically that sets potential energy 0 at infinity, right? And so the potential energy right at the surface of the Earth would be negative. Oh, excuse me, it would be something else. Is there supposed to be a minus here? Have I got that wrong? I feel like I got that wrong.
No, that's right. After you integrate.
Sure?
But it is supposed to be minus gradient.
If I differentiate this, I get minus. I think I'm supposed to have a minus there.
The minus gradient equals a minus GM.
Yeah, but that's the thing. This minus cancels. So I really have to solve this problem, right? Because the gradient of u just gives me partial u, partial r. So what I'm trying to say is this works out to minus du dr r hat. So the minuses cancel here, and you're just left with solving that.
Yeah, that makes sense.
And I don't think that that's plus. Check it out. Differentiate it for yourself. What happens when you differentiate 1 over r? Negative 1 over r squared, yeah. Okay, you guys should be happy that there's a minus there. Because if there wasn't, the solar system wouldn't be stable and stuff. So you'd be happy there's a minus there. Otherwise, it would be very troubling, really. I actually talked about this the previous day, right? So what's this, what's the plot of GMM over R minus? So if you look at that, oops. So that would be something like negative reciprocal, right? So here's R, here's energy, right? So for example, if my energy level is less than 0, again, setting potential energy to be 0 at infinity, I have a bound orbit, right? So as I told you before, these correspond to elliptical orbits. I can't spell the name. Orbit. And something up here would be so-called hyperbolic. Now, if the big M is the mass of the sun, I'm actually talking about the orbit of planets. If the big M is the mass of the Earth, I'm talking about the orbits of satellites. Right? But whether or not you have a bound orbit or an unbound orbit just depends on whether or not your energy level is enough such that you never bounce off the potential energy function in the energy diagram. So that brings us to a question, which is, how did we get away with MGH earlier? Right? How is it that potential energy is on the one hand MGH, but on the other hand this? How can it be both? Right? Well, the answer as usual is math. So let me work that out for you. That is always the answer. I guess there's experiment. Let's not let that cloud the issue here. Sorry. So I'm saying versus potential energy equals to minus G M big M over R. So in order to really understand this, we have to understand what R is. Right? R is this distance. Right? But on the flip side, we can also talk about this, which is the radius of the Earth, right? And then this, which is what appeared in our earlier formula, h, the altitude. Right? So, in fact, r is equal to the radius of the Earth plus the altitude. And so what I really have here is minus g m m over radius of the Earth plus h. And so I can do what can I do? I mean, this is a function. I can look at this as a function of I can look at this as a function of h, right? Think of this as a function of h. And I can use Taylor's theorem, right? I can expand and I can look at the Lorentz series in particular. I can look at f of 0 plus f prime of 0 times h, right? Plus 1/2 f prime of 0 times h squared, and so forth. By now, you guys have learned this because you're taking calculus too. I know this has happened. You can't hide from it. I know you know these things. Don't pretend you don't.
It's happening right now.
Yeah. Okay. It's happening right now?
That's what we're covering this week.
Which calculus is?
Dr. Joseph.
Okay. Okay. All right.
It's a new book. This is a new book also.
New book.
Yeah.
Okay. I guess this is just at the end. You already covered the rest of the material, I guess. Huh?
Yeah. This is the last thing we cover.
All right, that's fine. It's just usually, sometimes when I teach it, it ends up being like, there's stuff past that you teach, so you hit this earlier. But anyway, it's fine. Okay, so look at here. So what's f prime of h? It's g m over re plus h quantity squared, right? The minus goes away because differentiation of the reciprocal gives you a minus power, minus 1, and then the minus 2 power. So f prime of 0 is what? Right? And then what's f prime prime? Well, that gives you minus 2 g m divided by raised to the earth plus h quantity cubed. Right? And so f prime prime of 0 is roughly minus 2g m big M divided by the radius of the earth cubed. What's f of 0? So f of 0 would be minus g m divided by what? Just radius of the earth, right? So I have this term plus g m over the radius of the earth squared times h minus g m 2g m over the radius of the earth cubed plus da 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 da. This is an alternating series. See it? Plus minus plus minus plus minus plus minus. What do you know about an alternating series? What's the error in the nth term of an alternating series bounded by? Alternating series estimation test. You guys know this. The size of the n plus 1th term, right? So if I want to bound the error, in other words, the difference between this terms, so like the error in just keeping to the first term, say of f of h minus these two terms, so we call this thing star, minus star, that the order, the magnitude of that error is less than 2 g m over radius of the earth cubed. And oh, I'm missing an h squared, right? And I forgot to divide by 2, didn't I? So the 2 cancels and give an h squared. So that shows you precisely the error in just using the first 2 terms in the Taylor expansion rather than using the honest-to-goodness reciprocal law for the potential energy. That tells you how far off you could possibly be, that thing I just wrote down. It depends on the dividing by the cube of the radius of the earth and multiplying by the square of the altitude, right? And it's if you're heavier, right, it's worse. Because it does depend on little m as well as the mass of the earth. So, for one thing this says is that when you use this potential energy formula, the potential energy at the surface of the earth is not equal to 0, right? At the surface, this says that potential energy is equal to minus g m over the radius of the earth at the surface, right? In contrast, this guy has set the 0 to be 0 at the surface. That's one difference in these formulas. But the other more significant one, of course, is that this is linear in h, whereas that is reciprocal, right? what does this work out to? We worked this out the other day, right? So GM, remember we calculated this last time, I think it was? GM over the raised to the earth squared was like what? That was G. That's 9.8 meters per second squared. So this term actually is mgh. And then this is the correction term past it. You guys don't look convinced. Let me show you. I can. Give me a second here, I'll find it.
Should we know how to work this derivation for the test?
Well, since you asked, sure. It's not usually something I ask directly, but I do think this should be within your grasp. Yeah. But I never asked it before. I will tell you that. I mean, so statistically speaking, odds are against it, I suppose. But asking me the question, it does change the statistics slightly. Now you got me worried. Oh, you know, it probably works better if I hit the button. So if you guys look, I don't know if you do or not, but if you do, if you were to be so foolish as to look at my my Calculus 2 notes, or Calculus 1, I think Taylor's theorem should be covered in Calculus 1 actually. It fits naturally with the second and first derivative tests, honestly. Not everyone agrees with me. So, here I'm basically looking at functions and their Taylor approximations and graphically contrasting the Taylor polynomial versus the truth. And so here actually is but I decided to work it out for, you know, this is basically just the derivation I just went through with you guys, right? And I just put the numbers in, and what I figured out, well, like I told you, the error is something like, I'm missing an h squared. Oh man. Well, anyway, when I worked it out, got something like this formula for the error. So it's pretty small for a regular mass and a regular altitude. So once you got to an altitude of like 1,000,000 meters and a mass of a kilogram, your error would be about 3.1. And error what? I think I'm talking about error. I'm talking about looking at the we're looking at the acceleration here. Oops. Bummer. So I said if the altitude doesn't exceed 1,000 meters, the formula f over m equals g approximates the true inverse squared for about within 0.03. Once you get to 10,000 meters, the error is about 0.03. 100,000 meters, the error between g and the actual g is about 0.31. That's 60 miles. But my point is, if you understand this Taylor series stuff, you can actually answer, well, it's quantitatively how far off mgh is versus gmm over r. I wanted to make you aware of that because you shouldn't view Calculus 2 and physics as being disconnected events. They're actually part of the same toolbox of analysis about the real world, if you do so choose to make that analysis. Now, of course, that's a nasty test question, and I don't want to crush you guys, so I probably won't ask it, but that doesn't mean we shouldn't talk about it. And by the way, you might have noticed in the, do you guys remember in the note, in the lectures, where I gave an example using this? I'm trying to remember where it was. I think it was a while back. Man, where was that? Do you guys know what I'm talking about? There's a place when I was doing like motion on a plane, on a ramp, and I actually did the analysis for this versus that. Anybody happen to remember which lecture that was in? It was a while back, I think. If I had to guess. Ooh, guessed wrong. Probably wrong again. No, that's not the one. Do you guys want to take a guess? It's kind of fun. What's that? Lecture 1? Now you're just messing with me. A reasonable guess. How about it?
Wasn't it in when we were doing like, say,
It has to be involved.
translational kinetic energy?
It has to be after we introduce energy is the thing.
Yeah, translational kinetic.
Is it this one? I think this is not the one though. I know it when I see it. Sorry, I should have told you to take some medicine before you came to this one. We are looking at 16. This is your life. Here it is. Back in lecture 17, I contrasted these formulas. So here was the box up the plane using mgh, right? So the final energy is mgh right before it slides back down. So you could set 1/2 mv naught squared equal to mgh, and that will give you the relation between the height it goes up to before it slides back down, if there's no friction, right? And so you get that relation between the initial push you give the box versus the height, right? But here's the correct version. Correct version. I use this time the potential energy H is actually equal to minus GM/ME over R equals R equals H. There's an H. So kinetic energy is the final potential energy. Okay, this is an approximation. Right, I'm only taking the constant in the linear term. Oh, wait a minute, no. I took it exact. Excuse me. That's the exact formula. I added this term here. Why did I do that? If I add that term, excuse me, this term here, rather. I'm sorry, I misspoke a minute ago. This is H dependent, and this is a constant. I added, why did I add this constant? I added this constant to cancel out this, to make it equal to 0 at H when H is 0. So when H is 0, if I add this term, this is 0. See? This cancels that, you get 0. So when U of 0 is still 0. So it matches up with the MGH formula. Anyway, the reason I want to do that is so that I can say potential energy 0 at the start before the box slides up. So 1/2 mv naught squared equals the more correct version of the potential energy that involves the reciprocal. And then I do algebra, and then this is actually the height. The height depends on the radius of the Earth, as well as the mass of the Earth in that way. So I think you're probably happy that I lied to you earlier, because we could have been using this more correct formula all the time, but we wouldn't have been able to solve as many problems, right? Because the math is a lot more involved. Yep.
In which ways is the GM over R even not incomplete as still?
Oh, because Newtonian gravity only gets you so far. Newtonian gravity, for example, doesn't give any explanation for how is the Earth pulling on satellites? By what mechanism? By what mechanism does the sun pull on the Earth through gravity? It has this quote-unquote spooky action at a distance. To be more precise, there's no specific accounting for how the gravitational influence is propagated through space. There's no formal theoretical allowance for what exactly is a gravitational wave in Newton's theory. Right? So we have to have a deeper theory of gravity to understand that. And so one candidate for that that I think is relatively well verified with experiment at this point is general relativity, which actually does allow for gravitational waves. You can derive them, study their properties. I don't know the status experimentally of gravitational waves. We've been looking for them. We've set up these giant triangular. So the way it works is you have like a satellite here, a satellite there, a satellite way over there. We're talking like setting up huge, huge triangles, and then you have lasers between them, and then you can study what happens with respect to this triad. And if there's a gravitational wave that comes by, something happens, and you're able to measure it in terms of its distortion of the geometry of space. If space is curved, there's an angle deficit, or something like the angles in the triangle won't be 180 degrees anymore. For example, a pretty extreme example of this, if you have a sphere, right? And if you look at the triangle that's formed by the equatorial circle, and this great circle, and this other great circle, look at this spherical triangle, each one of these angles is right. So this triangle has 270 degrees interior. What? But a triangle, doesn't matter how you do it, right? Alpha, beta, gamma. We know alpha plus beta plus gamma is what? 180 degrees. Well, the reason we know that is because we are Euclidean geometers. We're used to flat space, where the sum of the angles interior to the triangle is 180 degrees. But when space is not flat, when space is curved, that's not true.
Isn't it kind of true to just like
I'm talking, yeah, that is true. You're perceptive. I'm talking about the curvature of three-dimensional space in a four-dimensional space-time. Yeah, that's true. So it's an analogy. But it's still true. The angle of a triangle in this curved space won't be necessarily 180 anymore. So something along those lines is what these large experiments could detect somehow. I don't know if we've actually detected gravitational waves yet. They have to be, you have to have like stupidly large astronomical events to produce waves that we can actually like measure. I mean, stuff like, I don't know, neutron star, like gets sucked into a black hole, and then stuff, waves go shooting off, basically, ripples through space and time.
So was there ever a gravitational wave that was detected?
Well, I don't know. I mean, it depends on how you want to interpret things. Are you sitting in your chair? So, I mean, we feel gravity, right? So, I mean, there's got to be. General relativity is successful in explaining Newtonian gravity, right? And you see the effects of Newtonian gravity all over the place. So, because general relativity does have a propagation of, the slogan basically mass curves space, and space pulls on mass. It's kind of circular, but that's actually how it works. It's nonlinear. So the presence of the mass of the sun, it curves space and time in such a way that the planets, they move along the space-time in what are called geodesics. That's paths of least distance. And that corresponds to actually them free falling. So free falling is actually motion along a straight line in this four-dimensional space-time. Anyway, I'm digressing. Guys, this will not help you with your homework. You should wait until you come and take our general relativity course here. So, ask those questions there.
Do we have one? We know.
No, we don't have a general relativity.
Would it theoretically be possible to force the curvature of space such that it had an eccentricity of some ellipse and something was swallowed by a bubble of space?
What if there were giant space whales?
They're giant space whales?
Four-dimensional space.
Yes. I don't know. You could go buy all the books of Mikio Kaku and read them. If anyone can explain it, you can. There are any number of popular books where you can read about these sorts of things, but if you want my serious answer to these questions, if you really want to understand general relativity, number one, you need to take Calculus 3. Number two, you need to take linear algebra. Number three, you need to take advanced calculus, because that's the closest thing I have to offer you here to tensor calculus. Number 4, you need to study manifold theory, differential geometry. Number 5, find a couple hundred hours, get a book on relativity, and work it out. That's really the only way you're really going to understand these questions. You can read what other people say for you to try to understand in terms of heuristic pictures and popular science books, but they're all lying to you. You can't really understand it unless you understand the math. That's just the cold, hard truth of it. You know, we used words for a couple thousand years, right? And we succeeded in convincing people with Aristotle and physics that, you know, heavy stuff is harder to push, and so it's going to fall faster also because it's heavier, right? And everybody's like, oh, that makes sense. I'll believe that. You know, it took a mathematical description to free us of the salesmanship of good-sounding ideas. I mean, math is the thing that keeps physicists from lying, all right? And so math is really important. To understand math, to be able to use it in physics, is to know physics. To not is to be subject to someone else's view of it. Simple as that. No. What I'm trying to tell you is math is freedom.
Math is freedom.
Yes. Math is intellectual freedom when it comes to analytical things. In the same way that having a gun is freedom when it comes to the local authority bothering you. You know, it's your natural defense. In the same way, when somebody tries to lie to you with numbers, if you're mathematically adept, they can't lie to you, right? You're a hard target. You say the statistics don't work out. I don't think calculus works that way. You know, energy conservation is in the way of your perpetual motion machine. Any other number of things people might try to sell to you. Physics is your ignorance or lack thereof is the difference between you being able to be sold something and not being able to be sold something, right? I digress. All right, so. Oh, I wasn't going to do that. Oh, I'm sorry. I'm supposed to work some examples. The Superman example, right? Superman, he throws. Let's see here. Superman throws.
If he has a gadget.
What's that?
Batman. We always use Superman.
We always use.
Batman is strong.
He can if he has a gadget.
Fine. In honor of the soon coming event, here's Thor. Takes his hammer. And we're just disregarding any Asgardian physics, which we don't understand nor can quantify. So setting aside Asgardian physics, we toss Thor's hammer. I mean, Thor tosses Thor's hammer because he's Thor. And, I mean, I know we can't. So suppose you toss it up with V naught equal to 5,000 meters per second. Straight up. Does it come back?
Well, it does because...
It's a loaded question. It's Thor's hammer. So I just want to...
The real question is how fast it comes back.
Right. I guess so. The question is, would Thor's hammer come back under the influence of Earth's gravity alone? The answer is, I don't think so. Let's work out why. So, if it comes back, what has to happen? There has to be some point where it turns around, right? And at that point, the kinetic energy has to be equal to 0. So the question is, can you even solve the equation kinetic energy equal to 0? So energy is conserved. So you have energy initially is what? So you have minus G M. I guess, would you guys want to make the energy at the surface of the Earth? It's your choice, I suppose. Let's just make it, I guess let's take our medicine. We'll use GMM over the radius of the Earth. There's the initial energy, plus what?
Now, why is the initial energy negative?
Because if we use U of R equals to minus GM M over R, right? The initial R is equal to radius of the Earth. In other words, gravitational potential energy is always negative if you use this formula. At infinity, it tends to 0, but it's never positive. Unless you choose a different constant. You can always shift the potential energy up or down. But with this formula, gravitational potential energy is negative. All right? So that's the gravitational potential energy as we're throwing Thor's hammer. And we also have the kinetic energy at the start, right? 1/2 m v naught squared. That's equal to what? Well, that's equal to minus g m over r squared, where r is an unknown. If it does turn around, there's a solution to this problem, and that r gives you the distance from the center of the Earth it goes to before it turns around, right? It doesn't give you the altitude. We still have to subtract off the radius of the Earth to get the altitude, right? But the question is, does that equation even have a solution? It doesn't have to. So students set this problem up on the final often, and they're like, I don't understand. I can't get a solution. It doesn't make sense. It does make sense. What you've just shown, this stupid thing does not turn around. There is no solution to this equation. This hypothetical is, in fact, false. So is that the case here? I don't know. We can cancel the m's, right? Cancel the little m's. Really, you just need to calculate this. Let's call this E naught. What is E naught equal to? Well, let's say what's E naught over m equal to? We got what? We got minus g mass of the Earth divided by the radius of the Earth plus what? V naught squared over m over 2. So you can plug in the numbers there and see what we get. Come on. Come back. Come back. Okay. All right, so big G I'm being greedy. So Earth mass. And what was A? What did they use for A? Equatorial radius. Mass. Well, should I believe it? So apparently this is minus 6.25. Don't do your homework this way. 10 to the 7. You got to use the numbers that are provided to you by the web assignment function and calculators, otherwise bad things will happen. I mean, not too bad, but so I think that makes sense. G is what? 10 to the minus 11. M is what? It's, roughly speaking, order of magnitude is 10 to the 24, right? Radius of the Earth was like 10 to the 6. So we got what? 10 to the, something like 10 to the, what is that? 24 minus 11 is what? 13 minus 6. 7. And then arithmetic, yeah. That's ballpark, I think it's right. And then plus, and it had units of meters squared divided by seconds squared, which is good. That's what we should have, because we got to meet the velocity squared here. So the dimensions make sense. It's helpful. So, well, 5,000 squared, which is what?
25 to 6 zeros.
Yeah, 25 times 10 to the, oh, it's 2.5, right? Divided by 2, so 1.25 times 10 to the 7 meters per second squared. Meters squared per second squared, right? And of course, you can see that that is less than 0. Oh, that's less than 0.
Yeah.
Oh, bummer. It is?
I thought the escape velocity was 7,000 meters per second.
I don't think that's right, because orbit is 8 kilometers per second. So you need to get 8,000 just to maintain orbit.
I think you guys are right. I was not greedy enough. Hey, but it's easy enough to see that that's less than 0, right? Which means that, in fact, we can solve, right? So the answer is just that this is not the case. It doesn't turn around. In fact, we can solve that. So you just put it back. Did I do this right? 1.25 times 10 to the 7th? I think so. So that gives us what? Minus 5.00 times 10 to the 7th is equal to minus G big M divided by R squared. And you just solve that for R. You get R. I have to do it up here. R is equal to, put it in the box. Let's see here. So what do we get? We get R is equal to the square root of, what is it? GM divided by 5 times 10 to the 7th, yeah. So that's the square root of, like, what is it, 6.67 times 10 to the minus 11 times 6 point, what was mass of Earth? I forget it already. 6.023? Well, 6.0 roughly speaking, times 10 to the 24th. Divided by 5 times 10 to the 7th, what do we get? G Aha. Oh, I forgot to put units in. It's like, it just treated this as a pure number because I told it a pure number, right? I'm like, what on earth? These are weird units. Yeah, okay, well, so what do we get? 2,000? That's it. That feels wrong.
2 miles.
It's not enough.
Well, I mean, the guy could throw a baseball on it.
No, 5,000 meters a second.
No, not 5,000, but if that'll only go maybe you know, who knows how high? Let's say 100 feet high. Doesn't it sort of make sense that
So let's just add a 0 to
a
it.
few miles would be significant?
50,000.
But shouldn't that R include the radius of the Earth?
Yeah, did I miss something here?
Maybe it's a Superman.
Well, yeah, that makes it worse, though. I mean, I have to subtract the radius of the Earth off of it. This is inside. I mean, that's inside the Earth.
Connected to black hole, I'm saying.
Yes, doesn't make sense. There's a miscalculation here somewhere.
When did the beginning difference didn't knock off the figures and not do that?
No, I divided by m because we don't know m. We don't care about it.
What is the minus G mm over R squared? What does that represent?
Gravitational potential. Oh, goodness gracious, guys. So this is the other mistake you guys make. As you can see, you rubbed off on me. Does this look like a potential energy term to you? See, next semester making this mistake, I will take all your points. So this semester, I'm just trying to show you not to do it. How it's confusing. It's nice that I did this on purpose for you today. You should value this pedagogical experiment that we did. But no, that's not supposed to be a square. That is no. That was the whole point today. The gravitational potential energy is the same formula, but with a minus and a reciprocal rather than a square in the reciprocal. So I don't need this square root. Is all that it really means for us here. I don't think I did do it on the other side, right? I just did it over there for some reason.
Yeah.
No one complained just yet. What's
We
that?
actually were wondering where you got.
Oh, you should ask me.
I just assumed
I've
that
already
was
just
stupid.
asked something.
Oh,
Yeah,
It's
that's
a waiting
just
period.
you just want to wait and see how long it takes me to unveil my pedagogy. Hey, come on.
That's significantly larger.
Oh, there we go. Yeah, 7.9 times 10 to the 6th. Oh, man. That's still small.
That's 5,000.
I wish I had a check this.
I don't like it. Fine. I still feel like I made a mistake here in the numbers. 7.97 times 10 to the what?
6.
Six.
And what's the radius of the Earth?
So, question, guys. What if you just shoot straight up, right, and ignore everything else, like, you know, gravitational attraction, the moon, and all that other kind of junk? Just the Earth, pretend it's sitting still, and you just shoot straight up. What's the minimum speed that you can shoot something straight up and not have it come back? You have to have, yeah, the minimum speed, right? You have to have this equal to 0, basically, right? So if you have this equal to 0, that means you can't solve this equation. And that corresponds to like being in the, what I call the parabolic case in the energy level diagram over there. So that would be, you know, if you wanted to solve that directly, let's do that. So, you know, I really wish there was about this much more board here. I would feel so much more civilized.
Right on the wall.
Right in the wall. Hey, maybe.
Well, then you cover it up with another whiteboard.
Yeah, that encourages them to give you more board space.
And then they cover it up with another whiteboard. So let's see here. We're trying to basically solve minus 6.25 times 10 to the 7th. Plus v naught squared divided by 2 equal to 0, right? So that gives us v naught is equal to square root, since we're looking for positive upward, we go to the minus. So we have what?
You can do it right there.
Yeah, 12.5 times 10 to the 7th, right? I mean, minus would correspond to the fact that you could just throw it the other way. If you somehow had if you drilled a hole through the center of the Earth, it would have
Well, that's interesting. Assuming there is something between, it will accelerate towards the center of mass, but then it decelerates away.
Next semester, I will explain to you guys why the Earth's gravity should decrease linearly to 0 as you go towards the center. Actually, it won't increase to infinity like the formula tells you. The formula gm m over r squared was only true past the surface of the Earth. Inside the surface of the Earth, actually the rule is something more like this. If the Earth was a big hunk of cheese, uniform density, it would look more like this. So linear. So the largest the force of gravity gets on the Earth is at the radius of the Earth. And then it decays off from there.
Is it just because you keep losing mass?
It's because once you're inside the Earth, the mass above you is pulling up on you, and only the mass below you is pulling you towards the center of the Earth. And it just conspires in such a way to be linear.
And therefore, when you hit the exact center of the mass, it's equal to 0, so therefore you don't get present.
That's right, in the exact center of the Earth, you'd be weightless. Zero gravity.
And sorry,
I'm losing just a second, guys. You guys are distracting me here. 0.5, which is fine, but
What's funny is that in that place we could study liquids and zero gravity.
what did you guys tell me? You guys are a repository of unnecessary facts and figures. I tell you, I'm very impressed. So, yeah, 11,180 meters per second, give or take, is the escape velocity, something like that. So as to make the problem interesting for the final, they usually just ask it on like a modified planet with like 1.5 times the Earth's mass, so that you don't just know this number and can answer it on the basis of comparison. Because I know you guys are usually anything to get around the math. I understand. I get it. Oh, you Googled it? Wolframed it? Very good.
Just on escape velocity.
I can respect that. But anyway, this is why, right? So this, having that velocity means in the energy level diagram, So here's the potential energy. What we're saying is that if you have that velocity, you're actually at energy 0. Which means you just keep going and going. Now you keep going slower and slower and slower away from the Earth, further away, right? So it's going to take you a really long time to get really far away. But nevertheless, your motion is not bounded. It just keeps going and going and going towards the comes back. Of course it does, because as you know, asteroid magic makes it come back to yes.
So if it's exactly at that speed, it'll just keep going.
Yeah.
Although technically, if you could throw it precisely enough, if you could throw it precisely enough, couldn't you have it stop? Well, that would have to stop it.
You can have it stop. You can throw it precisely enough. You can have it stop as far out as you want. Come back. You can always.
But it always would come back until you get to infinity.
Really make it stop right there. But yeah, it will come back once it hits that. It bounces back.
Is it really affected by gravity if it all just goes back to full center?
Anyway, I shut up. Hey guys, you know where we're going? Next Monday and Wednesday, I am completely devoted for your website questions. Of course, Thursday or Friday you have the test. Then Friday next week and Monday of the final week, I will talk about relativity. So of course, the chapter 37, the relativity, like 2 questions, I'll push back to reading day so that you can answer them then. And that will be on the final, but it's like 2% to 5% of the final or something. And most of the finals on test 1, 2, and 3, of course. And we'll talk more about what's on test 3 next week.